Hello, my name is Tom Ralph, and today I'll be presenting my work on the behavior of additively manufactured Inconel 718. This work is part of the online RAU program at Texas A&M University and was supported as well as having materials provided by the Aerospace Corporation. This work was additionally supported by the U.S. Department of Energy National Nuclear Security Administration. Inconel 718 is a widely used metal alloy in aerospace. It's often chosen for roles due to its high corrosion resistance, weldability, and elevated temperature behavior. Selective laser melting is an emerging technology that uses a controlled laser over a powder bed to additively manufacture metal samples. A diagram of how this works is shown right here. Additive manufacturing makes manufacturing metals easier and faster. In addition, compared to traditional metal manufacturing methods used in the aerospace industry, additive manufacturing can reduce waste material by up to 90%. Selective laser melted samples of Inconel 718 have shown similar behavior to traditional wrought samples at room temperature. However, tests have shown that the selective laser melted sample performs poorly at high temperatures. This is particularly apparent in creep, high temperature tensile, and notch resistance tests. This graph right here shows a slow strain rate tensile test undertaken at various temperatures by the Aerospace Corporation. As can be seen, at each of these temperatures, the wrought material performed significantly better than the selective laser melted sample. Explaining this behavior is the goal of the current research. The reasons that are currently predicted to be why the selective laser melted samples are failing quicker are differences in the microstructure. First, the wrought material will have larger and more widely spaced niobium carbide particles. This can be seen in these diagrams by the white arrows. Right here we can see that in the wrought sample, there's only one niobium carbide particle shown, but it's very large. On the other hand, in the selective laser melted sample, we can see these particles are much more numerous, however significantly smaller in size. Another important distinction seen is the formation of the delta phase. In selective laser melting, this forms along the grain boundary, whereas in wrought samples, it's seen forming radiating from the interior of grains outward across grain boundaries. This can be seen in these images as the red lines. Here on the selective laser melted sample, we see these thin lines of delta phase particles forming smoothly along grain boundaries. However, moving over to the wrought sample, we see no such constraints and they break several grain boundary lines. Another important feature that has been seen in tests is that after tests, there are increased intergranular failure rates on the selective laser melted samples. So our goal is to confirm the presence of these features so that we can link them to the macroscale behavior in our samples. The analysis was undergone on an optical microscope on polished samples of both wrought and selective laser melted sample. As can be seen, each of these have a scale of about 100 micrometers. The particles shown in white appear to be inclusions on the metal, specifically the niobium carbide particles. They follow the expected behavior of these particles. First, we can look at the shape and amount of these particles. They follow the pattern of smaller and more numerous inclusions in the selective laser melted as compared to the wrought. Here we can see that there is significantly more particles, but each smaller size. We're moving over to the wrought, we see only a few of these much larger particles. Another important consideration is the distribution of them. On the selective laser melting side, we see these are much more tightly packed and kind of formed in little groups. Comparing it over to the wrought sample again, we see that they're very evenly distributed and there seems to be no such patterns present. Confirmation that there are far more niobium carbide particles in the selective laser melted sample, as well as them behaving so differently, provides strong evidence that this is a key reason for the difference in behavior at high temperatures. So having done that test, where can we look forward? The first step would be to move to electron microscopy so that we could assess the microstructure in more detail. This would allow us to look more closely at the behavior of those identified niobium carbide particles on a smaller scale. In addition, it would allow us to see other features of note, such as the delta phase or the grain boundary fractures that were discussed earlier. Linking the locations of these, as well as identifying them, could provide more insight and include how the relative distance of these might have compounding effects on the material failure. Another place that this research could be progressed would be going to nanoindentation. This would let us link the nanoscale hardness to the behavior at the macro scale. And additionally, we could measure the hardness near key features in the metal. One of these would be to look at the differences of grain boundary hardness, considering the different ways that the delta phase forms. Another, more related to the current research, would be looking at the niobium carbide particles. We could look at the hardness of the specific particles to see if they're significantly harder or softer than the regular metal. In addition, we could look at the areas around it. As shown, the selective laser melted sample has far more numerous and tightly grouped niobium carbide particles. There's concern that these could be leaching elements from the surrounding metal, and we could see if that is causing a significant difference in hardness around it. This could indicate that dynamic embrittlement is at play for causing the high temperature failure. These tests, in combination with that I've already conducted, could help to identify which of these variables is most critical when trying to improve and identify the high temperature behavior of selected laser melted Inconel 718. In conclusion, selective laser melting can improve manufacturing capabilities and reduce the cost. The presence of increased niobium carbide particles found in the selective laser melted Inconel 718 in this test indicate a strong link to the change in failure. A nanoscale analysis could be undertaken to uncover the mechanisms behind this failure. I'd like to thank my collaborators, Dr. Jean-Briac Legrevand and Dr. Michael Dimkovich from Texas A&M, as well as David Witkin and Tate McLouth from the Aerospace Corporation. Thank you.